So now it's your turn. Now it's your turn to try to simplify radicals. At this point, you should have completed the Your Turn problems, and now we're going to review over them to see how you did. The first problem you were given was to simplify the square root of 32. So we're going to start with that one, square root of 32. Now when you simplify this, you're looking for the twins. Again, you want to think what two numbers multiply together to give you 32. Well, if we do 16 times 2, that will give us 32. And 2 is prime, so we can circle that. Now if we think about 16, 16 is 4 times 4, which technically is a twin, and you could stop right now. But if you wanted to go all the way to the prime factorization, we'd keep going. And we'd go ahead and say 2 times 2 is 4, and since both of those are prime numbers, now we can circle them. And the same here, 2 times 2 is 4. So basically now for the square root of 32, what we have is 5 2's, and we're going to multiply them all times each other. So 2 times 2 times 2 times 2 times 2. And the index of this, since it's not there, implies that it's a 2. So we're looking for sets of 2. So when we circle our set of 2 here and our set of 2 here, we only get to pull out one of each of them. So that means I'm going to be pulling out 1 2 from here. So I pull that out and say there's a 2. Then I'm going to pull out another 2 from here, and that's going to come outside, and we're going to multiply that together. And now we're done with that. Now we have the radical, and what's still left inside is a 2. So we'll clean this up. On the outside, our coefficient's going to be 4 because 2 times 2 is 4. And then we have square root of 2, and that would be our final answer. In the second problem you've been given here, you've been asked to simplify just variables inside here as our radicand. So we have x squared times y, and we're taking the square root of it. So you can think of this two different ways. The first way is to go ahead and think about expanding this out. X squared means x times x, and we still have times y. So what we're looking for is our set of twins because our index is 2 again. If we circle this, we only get to pull out 1 when we pull it outside, so we pull out the x, and now we're done with that. Still inside without a buddy would be the square root of y, and that would be our final answer. But the other thing I want to point out is the way you could have thought about this was when you had that square root of x squared times y, and the index is 2, you want to say how many times does 2 go into this 2 right here evenly? And it goes in 1 time. So it's x to the first power 1 time here. And then do we have anything left? Was there any remainder? There wouldn't be for that x. So then we go to the y and we say how many times does 2 go into 1 evenly? And it doesn't. So that would have to stay inside. And then anything to the first power is that number. So x to the first power is x square root of y. Either approach can be used, but the advantage of using the second approach is that when you get to really large numbers that have really large exponents, it's very beneficial to actually have this strategy to use, which we'll see actually in number 4. Let's go ahead and go to number 3. Number 3, we were given the problem, the cube root of 1080. Now, in this problem, we're going to again want to break this down with prime factorization. So we want to say, well, that's even, so we could put a 2 into it. So we'd say, hey, 2 times 540 would give me 1080. 2 is prime, so I can circle it. I notice that 540 is still even, so maybe I want to divide a 2 out of it again. So 2 times, this could be 270. So 2 is our prime number, so we can circle it. Still, I notice that it's divisible by 2, so I'm going to keep going. So then I have 2 times 135. So I circle my prime number. Now 135 is no longer divisible by 2, but since it ends in a 5, I do know it's divisible by the number 5. And it's 5 times 27. 5 is prime, so I can circle that. And now 27 would break down into 9 times 3. 3 is prime. And 9 would break down into 3 times 3. And now we're down all the way to the prime numbers. So let's go ahead and rewrite this. We have the cube root of, we're going to put this in numerical order. I see 3 2's, I see 3 3's, and I see a 5. And notice our index here is 3. We're looking for sets of 3. So here's a set of 3. Here's a set of 3, and remember, the same rule still applies. You only get to pull one outside. So I only get to pull out one of those 2's, and now I'm done with that. I only get to pull out one of those 3's, and now I'm done with that. Notice I'm multiplying on the outside. Still on the inside would then be the cube root of 5. So to finish this up, we just have to do 2 times 3, which is 6, and that would be multiplied times the cube root of 5, and that would be my final answer right here. In this last problem, we're combining both numbers and variables, and we're going to do the square root of 60 times x to the 23rd power. And this is a great example of not wanting to write out 23 x's and looking for their twins. There's a shortcut. We are going to first start with the number. And that number right there, if we want, we could say that's even, so it's 2 times 30, so 2 is prime. And then with 30, we could say, well, that would be something like 5 times 6, and 5 is prime. And then 6 could be broken down into 2 times 3, and both of those are now prime. So now if we think about this, and I'll go ahead and show you with the square root of 60, I'm putting that in numerical order. We have 2 times 2 times 3 times 5, and then we can't forget that we still have x to the 23rd power. So from here, what I'm going to do is I'm going to look for the twins, and what I've got for twins, because our index is 2, is I got a set of 2's, and only one of those gets to come out, so we keep the 2, but now we're done with that. Now, in terms of the 3 and 5, neither one of those are twins, so we're not going to take either one of those out. They're going to stay inside. However, if we come to the x, we got 23 of them. And this is that idea of, since the index is 2, how many times does 2 go into the number 23 times evenly? And it would actually go in 11 times. If you need to think about it this way, it's like you're saying, hey, I've got the number 23, and I want to see how many times 2 goes into evenly. So we say 2 goes into itself once. 1 times 2 is 2. Then we subtract, we bring down the 3. 2 goes into 3 once. And then we multiply here, and I have a remainder of 1. So notice it goes in 11 times evenly. Then we have the square root that we're going to come back to. We still have 3 times 5, which is 15. And do you remember how we had a remainder of 1 over here? Well, when we had the remainder of 1, that means I still have 1x left inside this radical as part of the radicand. And this would be my final answer. So in this module, there are a few things that you want to make sure you remember. First, when you're using this method to simplify radicals, you want to start with the prime factorization of the number. Look for all your prime numbers that multiply together to give you the number that's under the radical symbol, called the radicand. You want to make sure you pay attention to the index. That's the number on the outside. Like in example number 3, we had a cube root, so the index was 3. The rest of them, when there is no number on the outside, it's an implied 2, so you're looking for sets of 2. Finally, when you remove a set of numbers, make sure that when you remove it to the outside of that radical symbol, you only keep one of them. No matter how many you're taking out, then what you'll do is you'll take one from each set and multiply what's remaining on the outside and what's remaining on the inside to finalize your answer.